Introduce the next speaker, a special honor from my side because it's a colleague of mine from the Fraunhofer IGCV in Germany. I would like to introduce Jakob WOELLING. He's the head of the department for recycling of composites, and his presentation is about the recycling of carbon fibers. So Jakob, the stage is yours. And just remember the 20 minutes, we're a little bit over time. I think the JEC is closing in Korea and we don't want to let the people be there after closing.
I'll try my best. Thanks a lot. So I hope you can all hear me and see me. And I think you should also be able to see my screen now. Oops, I think that's the wrong order. Okay. I'll try again. So now it should work, I hope. Yeah. Okay, so thanks for the introduction, Frank. I'm happy and honored to present some results of the project ScrapSeRO to you today. So let's jump right in. A short agenda. I think I'll give you a short motivation, but as it's all about the project results, the main focus will be on the work packages and the description of the work packages itself. So I think the overall motivation for recycling of composites or carbon fiber reinforced composites is quite obvious. The market is strongly growing, and alongside with that also the amount of carbon fiber waste, end-of-life waste, as well as production scrap. So we need to develop technical solutions to that, but that's not all of the story, because even if the technical possibilities exist, we still need to bring them into service. And here we see a lot of challenges alongside, because we have very different national framework conditions. For example, disposal guidelines, what is allowed in which country and what is not, and so on. So we need to develop the expertise and also transfer it into as many countries as possible to provide the possibilities to handle with these waste materials. And that's also a big point within the project ScrapSeRO. So it's both the technical solutions or the development of technical solutions, as well as the setup of an international network here. So if we look at the state of the art for carbon fiber recycling, we see, let's say, an unfavorable price-performance ratio. We have rather high cost compared to virgin material, not higher than virgin, but still in the same order of magnitude. But we have rather low mechanical performance compared to virgin carbon fibers. So this is where we are, and from here there are two main possibilities. You could go and try to push down the price as low as possible and remain with the mechanical performance in order to repair the price performance ratio. But that's not our definition of recycling. That's just downcycling. So we try to aim to push the mechanical performance as high as possible. And here we see the production of nonwovens is possible at the moment already, but we have two major drawbacks for the mechanical performance. And that is, on the one side, the low fiber volume content. Current state-of-the-art products have, let's say, 35% fiber volume content, and we have a very little fiber orientation at the moment. The good thing here is that these two go hand in hand. So if you manage to bring fiber orientation up, you can also increase the fiber volume content significantly. So that's one of the major focuses here. And then we look at the entire process chain all the way down from fiber placement, consolidation, and so on. So not just the semi-finished product, but all the way to a second life, second generation part. We look at the wetlaying process because we see one big advantage in homogeneity and the easiness of the process to also handle with 100% recycled carbon fibers, which is not as easy as you might think with other processes, for example, textile processes. It is possible, but you need to be very aware of what you're doing, and need to be in full control of your machine and perfectly know what to do. So it's not as easy, and wetlaying technology has a lot of advantages here because there is not so much damaging of the fibers, and it's a much more fiber orientated process. But I think it's both alongside. So you need the textile processes for longer fibers and the wetlaying technology for shorter fibers. So it's both technologies will be necessary at the end of the day to handle with all the different materials that come from CFRP production, scrap, and end of life as well. The challenges at the moment are that currently there are mostly isotropic products available, and we always face the question of whether or not we need some additives in the process, some dispersing agents, for example, and will they at the end interfere with the following process steps? For example, will they decrease the availability of impregnation? Will they cause voids and dry spots within the second generation part? So that's a big question that we look at. And also how to continue in the following process steps with products with a rather low weight per unit area. So that's the bigger, the one advantage of the textile processes, that you can produce higher fiber volume content, higher aerial weight in the semi-finished products. And we developed the process chain for rather thin plies and see if they can be brought into process into service as well. We look at the full profitability of the overall process chain and how stable will it be at the end, because a lot of things work on lab scale, but if you try to bring them into full scale production, then things look a lot different in a lot of cases. So here are some main key facts put together. The project duration is 3 years. At the moment, it would end at end of April next year, but we are just currently in discussion with the funding agency if we can extend the project duration up to December 22. And at the bottom, I think that's more interesting, are all the partners that are involved in the technical development within the project. What do we actually do in the project? The actual work package structure is a little bit more complicated, but I think it's okay for today to summarize it as follows. So first of all, we start with the development of nonwovens. Here, the main focus is on fiber orientation and homogeneity and stability of the process. So we select fibers and matrix materials suitable for this process and suitable for all the following process chain steps, and try to make an as good and as highly orientated nonwoven as possible. Then in a second step, we continue with pre-pregging. We have both routes involved in the project. So we look at thermoset and thermoplastic materials, and we look at a continuous production line here as well. Then in a third step, we look at automated production technologies for such continuous materials, because it's not only about hand layup. We have some hand layup as well in the project to get some first results, to get some mechanical characterization. But at the end, we want to develop a material that is capable for full-scale serial production. And of course, alongside, we do a lot of characterization as well, inline and offline. So to each of these steps, I will go a little bit more into detail. So here you can see the lab scale paper line from the company Voigt, which is one of the partners. Voigt is a machine manufacturer for paper machines, and from looking at paper industry, this machine is a small lab scale machine. If you look at recycling of composites, of carbon fiber composites, you could imagine this being a full production, full serial production scale line. And Voigt does a lot of development here, and we look at the influence of the different processing parameters. As you can imagine, you can adjust a lot of parameters within this machine, and we'll at the end look how will they turn out in the nonwoven, in fiber orientation, in homogeneity, and how does this again influence the final properties of the part. We have already proven within the project that we can continuously produce nonwovens by this, and we have also proven that we can, if desired, go to a full isotropic property of the material, orientation from one in machine direction to one in cross direction. But in a first shot, we have already proven that we can go up to 2.5 times as much orientation in machine direction compared to cross direction. So fiber orientation is possible within this process. The 2.5 is not the end of the story. This is not where we want to end, and we want to see how high we can push this value within the remaining time of the project. Alongside to this quite big machine, we have one smaller wetlaying machine at our institute, at the Fraunhofer, where we, as the machine is smaller, we can go more into detail, we can go more into fundamentals, we can look at the different process parameters here as well, the difference in speed between suspension of water and fibers and the production wire. We can go more into detail in material selection, in the compatibility of the binder and the resulting matrix, the adhesion between those and the resin impregnation, and also the resulting mechanical properties. So this machine was just set up last year and during this year, and it's at full operation at the moment. Then in the next step, we have the continuous production of prepreg materials. As mentioned before, we look at thermoset and thermoplastic materials. For the thermoset, we have two partners, which is Sika and Lamilux. Sika is a resin developer that adjusts their resin to the specific needs within the project, to the already mentioned binders, to the curing temperatures and storage temperatures desired for such a recycled prepreg material. And we have Lamilux, which is a producer of such continuous materials, rather being wet prepreg or cured panel material. And we have Covestro. They cover the thermoplastic route. They have PC material, PC film, and we stack it with dry 100% recycled carbon fiber material. And by the sequence of stacking, we can adjust fiber volume content and the amount of resin and so on. So those are the two routes. Both are in a continuous state. Here at the bottom, you can see the small sample plates that we did in hand layup for mechanical testing, but this was just for a first shot to see how the mechanical properties turn out. And at the moment, we are working on the continuous line in both processes.
Jakob, you have 2 minutes left.
Okay. Then we have Brutier Automation. which is a manufacturer of hardware for continuous tape laying machines, and they have adjusted one laying head in order to handle the materials that we will develop within the project, because it's not commercial slit tape that we have here at the end. We have some wider tapes here at the end, and there were some adjustments necessary, and this head is also fully operational now, and we are just doing the validation tests at the moment. So this is also work in progress. And finally, we do some characterization alongside, because fiber orientation is key, but how good is the orientation? How much orientation do we have? And in order to answer this question, we need to measure it first. And here we have the sensor from the company Suragus, which is also in the project. And here you can see the measure signals from an orientated product with higher measure signals in 0-degree direction and lower signals in 90 degrees. And this works as well as a standalone measurement device, but we have also implemented in the production line, and we can track the properties during production in line. And then we do the mechanical testing. Here are some first results. As you can see, we have a rather low fiber volume content, but this was just to be sure that we have something that we can produce in the end. In the remaining time, we will also go for higher fiber volume content. I think you can have a look at these numbers faster than I can read them out to you. So yes. And then at the end, we will have a common demonstrator between Korean partners and German partners. At the moment, we are just sending material over to Korea. And then we will discuss how to continue with the production. At the moment, it is planned to have a demonstrator for the roof of the I-30N. At the beginning of the project, it was planned to have a common exchange, regular exchange, that we travel to Korea and vice versa. Then it was COVID and everything changed. So at the moment, we are limited to virtual exchange via Teams and chatting once in a while. We are planning to repair this as well, and perhaps spring next year we will be able to send our personnel to Korea and then have some more personal exchange and sharing expertise on the project. So here are my contact data for anyone who wants to get in contact afterwards. And finally, it's time to say thanks to all the funding ministries and funding agencies and the cluster management, and also the audience, to all of you for listening and for spending the time with me. Thanks a lot.
Thank you, Jakob. I think we have time for one question from the audience. So if there's a question, feel free to ask.
Is there any question from the audience? It seems like there's no question. Thank you very much.
Then, I have one question, Jakob, from my side. What do you think is the highest possible fiber room content you can reach with those materials you mentioned?
So at the moment, we went for the safe values to be able to show the full production steps throughout the entire project, not to run into a dead end here. We have seen that it is possible to go to 50% and higher on lab scale. And I think it will be part of the project to see how far we can push this technology from lab scale into serial production, because this lab scale fiber volume content was on a very narrow tape with a couple of millimeters of width, which is far beyond serial production. But there we see values above 50%, and we need to see if we can bring this into full-scale production.
Okay, thank you. There's one question in the chat, maybe shortly. For the recycled carbon fibers, how short or long are the fibers that you are managing for the wet lathe?
So the wetlaying is typically working with a range from, let's say, even below 1 millimeters up to 30 millimeters, but these are the extremes. So below 1, it gets quite difficult, and above, let's say, 20, it also gets difficult. So anything between 2 and 20 millimeters is where we feel quite comfortable. Everything besides that, we have to take a look.
There's another question regarding the aspect ratio, but I think the diameter is just 7 microns and then the length that you mentioned.
Yeah, the diameter is rather untouched within the entire recycling chain. So we typically have fibers from pyrolysis, and if pyrolysis is done correctly, then the diameter remains at 7 microns, and there is no decrease in diameter.
Okay. Okay, thank you, Jakob, for the interesting talk.
Thanks a lot.
We go on to the next speaker, the last speaker of the day and of the session.